The Ukrainian AI community used to create, develop, and educate for a shining future. But then Russia ruined our peace. We switched to a new reality. We do our best to defend our country. The brightest AI minds came to share knowledge with us. Together, we will build a technological and secure future. Peace in Ukraine equals peace in the world. Support Ukraine. Support the AI community.
All right, welcome to AI for Ukraine. This is a series of workshops and lectures held by international AI experts to support Ukraine's tech community in the time of war. We do the best we can for our family, colleagues, friends who are there at the front lines as warriors, paramedics, volunteers, and fundraisers. I, for one, feel a great pride to say thank you for your service. You, my dear audience, can also say thank you by simply donating for our cause. I am pleased to announce that last week we hit 300,000 UA hryvnias in donations, which we forwarded to the biggest Ukrainian foundation, Come Back Alive. Please keep donating and hitting your donate buttons as our plan is to double, triple, quadruple, quintuple, whatever that amount. My name is Dr. Daniel Einor. As you can guess from my last name, I'm pretty much related to the topic. I work as a data scientist at SoftServe, and it is a great honor to be the host for you tonight. No more words about me, as today we have a lecture from Dr. Anna Rohrbach, where Anna will tell us about multimodal grounded learning with vision and language. My helper fairies will let Anna in a few minutes. Meanwhile, let's briefly get our hands on the tool which we're going to use for the questions during the live stream. Please follow the website called slido.com in your browser and put the code AI for Ukraine. And also, please use your preferred name and email. Alternatively, use your smartphone to scan the QR code that you see on the screen now. If nothing works, simply follow the link which you can find under the video. All right, let's test it together. Today's question is how familiar you are with today's research topic on the intersection of vision and language models. Let me start a poll, and please vote and let me know your thoughts. While you're doing that, please let me invite Anna to the scene. Hi, Anna. How are you? Good morning.
Hi, everyone. Good morning. Great to be with you all today.
Thank you. It's a pleasure to have you here. Anna is a research scientist at the University of California, Berkeley. She has completed her PhD at Max Planck Institute for Informatics and received Otto Hahn Medals there in 2017. Her research is at the intersection of vision and language. Recently, she is focusing on building explainable models, addressing bias in existing vision language models, detecting semantic mismatch in context of multimodal misinformation. Anna is a recognized researcher and outstanding reviewer at CVPR, at NeurIPS at ICCV. As well, Anna is serving as an area chair of NeurIPS datasets and Benchmark 2022 and ICCV in 2021. Anna, welcome.
Thank you so much. Thanks for the intro. I'm looking at the poll. Looks like we're gonna learn a lot today.
Yeah, lots of people want to learn about your topic. That's exciting. All right, I am off. We will be back for the QA session.
Okay, so I hope you can see the screen. Maybe could somebody give me a heads up on that? That the screen is
all good. We can see it.
I'm assuming we are good. All right, so let's get started with the multimodal grounded learning with vision and language. All right, so looks like we have an audience with mixed levels of expertise in this area, but mostly people who I would say are more novices in this area. So I will try to go a bit slower over some of the more technical parts, but hopefully at the level that everybody can understand the main ideas. All right, so let's start with the observation as follows, that AI is arguably already everywhere and already impacting our lives in the most sensitive environments or aspects of our life, from healthcare to assistive technology, such as assisting, say, visually impaired users, to, in the very near future, self-driving, which can be obviously a high-risk domain, to our homes, smart homes and other home assistants, which we let inside our sort of home environments. And so what all of this suggests is that what is going to be important is that we can establish more human-like interactions with AI so that we could understand what AI is doing, what decisions it's making, why, and it can communicate back to us. And we could build sort of a more appropriate trust and understanding of these systems as they become really omnipresent in our lives. So we'll be talking today mostly about multimodal learning, since we all live in the world which is multimodal, and the primary two signals of interactions that we have is through vision and language. So how do we as humans interact with each other? Let's see this example. So, for a mom and the daughter who are walking on the street here, they see this bird. And so the little one says, look, there is a blue jay sitting on a branch. So this is something we do naturally. We explain what we see around us, what we see in the environments that surround us, or either embodied or real. Also, we ground a concept to the common reality, so that actually allows us to understand each other, so that one person's blue jay means the same thing as the other person's blue jay, so that they can understand that it's about this bird. And we know what's the branch, and we know all these things. So we ground them to the same reality we all share. And last but not least, we also learn from each other from just language. So the mother could say, did you know blue jay like eating acorns? And this is not something that we are immediately observing, but we could easily imagine what such a situation could look like. And that would enhance our knowledge about this concept of blue jay, and also enable us to recognize this situation if we ever see this in real world. So these three capabilities, to communicate, to ground, and to learn from language, I argue are also important to enable within our human and AI interactions. And so these three are high on my priority, high on my wish list of things that I want the kind of AI of the future to be able to do. So in the following, I'll try to convince you a bit more about why these three are so important, in particular for human AI interaction. And we'll dive into each of these three skills in the following slides. So communication. Like I said, a very natural example is we have a visual scene and we want to produce some description of that scene. So visual captioning. Many of you may have seen over the years a lot of work showing how you could automatically caption images and even video these days. There has been a huge amount of progress in that area. And there are many important applications, for instance, assisting the visually impaired users. However, what we have seen less so is a more human-centric angle, such as generating explanations. So if you have a model which can recognize the different bird species, it could tell you this is a blue jay. You might also want to hear from the model why it thinks that. So is it because it's a blue above and white below, this prominent crest? So if you could know that your model actually understands and recognizes all these properties, it will communicate to you much better what the model is seeing, how it is thinking. So ideally, these explanations should be faithful and introspective into how the actual model operates. And as a result, we would build appropriate trust with our models, because we would know how they think, maybe how they fail, and we could then reason about whether to trust them or not. The second very important aspect is grounding. So again, from a more formal perspective, there is the task of visual grounding studied over the last decade. We could just see this as a localization of things expressed via language back into images, like localizing short phrases, a blue wing, a black beak, etc. And there is a lot of interest in that space recently in scaling this up, to an open vocabulary settings to ultimately enable open vocabulary object detection as well. However, again, another perspective, and if we again take a more human sort of centric approach here, grounding is just an alignment between the two modalities, which we expect to kind of emerge in our models, especially if we train multimodal models. We just kind of expect that they relate the words to the right places in the image. However, in practice, that's not often the case. So in this example, there is a caption, a bird sitting on a branch, but there is no bird. So perhaps what happened is that the model got biased by the branch and the sky and the trees, and it hallucinates this bird over there, which is not present. So the grounding is not really working. And as you could imagine, this could lead to very serious problems and biases in real world applications. Not all of these could be benign, but could be some really harmful scenarios as well. So lack of grounding would hurt actually the user. So clearly important for human AI communication and interaction. So last idea, learning from language. Essentially, again, one way to think about this is language provides us a lot of knowledge. So we could leverage language to do things like zero-shot learning. And this isn't a new idea, but people have been exploring the use of language, such as in the form of attributes, for a while now. So for example, you want to recognize the species, you would ask an expert, tell me what attributes this particular bird has. You would just kind of enumerate them and use that as external knowledge to then recognize new species which you've never seen before. And recently we are seeing with the advancements of large-scale models, which have been trained on millions and millions of image caption pairs, that we could scale this paradigm to we no longer require experts, we just leverage this huge amount of knowledge sort of obtained online to do similar things. At the same time, a more human-centric approach, again, is to think about learning from language as this idea of advisable learning. So we humans, we oftentimes learn not just by experience and doing things, but also we learn from rules. Somebody could tell us what's the right behavior, what is to avoid. We could read a manual about how to do something. So we could learn simply by reading and listening to other humans. And similarly, we could start correcting and improving model behavior through language. So consider the example here. There is a bird in an unusual context. It is swimming or in the water, partially submerged. And so if our model was trained to recognize what bird category this is, it might be confused by the presence of water. And if you could tell it, look at the bird, not the water, perhaps it would help it to understand what species this is, and say not be confused with a duck or some other bird. So we would like to correct the undesired model behavior, leveraging this sort of textual linguistic advice. And again, you could think how this is super important for any real world applications where a user or a developer may encounter such undesired behavior in the model and may want to address it by simply telling the model what not to do. Wouldn't that be wonderful? And so this brings me to this sort of key message of this presentation is I want to build AI models that can communicate, that are grounded, and that can learn from language. And we'll talk today about all three of these important skills, but not in isolation. We will actually talk about the different interplays and interdependencies between these. So in particular, we will start by discussing how communication needs grounding. You cannot just communicate without actually correctly localizing things you're talking about. Second, we'll talk about how even with grounded communication between human and AI, you might still need to correct the AI's behavior with advice, like we just saw in the previous example. And then in the following two parts, we'll talk about this broad idea of learning from language, how it could be instantiated for improving visual robustness of our vision models, and for visual transfer. So that's the plan for today. Let's dive into the first part, communication, with language. There you go. So we'll talk about captioning for a while. So this is the task, like I said, of captioning, of producing captions for images. And so here's an example of a state-of-the-art, very recent captioning model, OFA, which given such a photo very confidently says there is a man flying through the air while riding a snowboard. And maybe some of you say, well, what's the big deal with this caption? Well, in truth, we couldn't tell if there is a man or a woman in this photo. And this is not a single example. There is many examples you could try sort of doing this, where the model simply believes that it's much more common to talk about men, in a particular context, such as riding a snowboard. And
Hey,
we as
Anna,
humans
I'm
maybe
really sorry
don't
to
say
interrupt
that
you.
in this particular way. We might say there is a person on a snowboard because we can't really see. And so basically
Anna?
what I'm saying is that the models talk about gender even when, was there for a moment a blackout?
I'm sorry. Yeah, I'm sorry that I have to interrupt you. The slides went off. Can you please reshare them?
I wonder why that happened. I kind of, I didn't really see any, I didn't touch the interface, but may have clicked somewhere accidentally. Okay, so
all right, it's going up.
We are looking at the example. Yeah.
Perfect.
Yeah, I might have accidentally
Apologies.
clicked on the UI for stop screen. That might have happened. There's too many things on my screen. All right, so we talk about these examples, and I just show them again so that the images like these, where you can't really tell who the person is, and the model still is quite sure that this is a man, for example. So what we started exploring when we saw this issue is that the models don't only capture the already existing imbalances in the data, like there is more men than women in our captions, but they actually tend to make the issue worse. So they exaggerate that imbalance. So we are predicting even more captions with men than women. So why is that? So here is another example, just kind of zooming in a bit into this. Here is this lady at a computer at her house, most likely. And so a caption says there's a man sitting at a desk with a laptop computer. So clearly it's misclassifying this person. What we found is that the model, if we look into where it's actually attending to, isn't even paying attention to the person. It is completely oblivious to this person. It just sees a monitor. And based on some correlations in the data, perhaps it thinks, therefore I'm going to talk about a man in the scene. That's our hypothesis, that this is an issue of basically grounding within this model. Now we found a second example when the model is accurate. It says there is a man holding a tennis racket, but it still wasn't looking at the man. It was looking at the tennis racket. So clearly there's something going on with our model not attending to the person when discussing their gender and so on. And so we want to overcome this problem to make the model say the correct word, but also we want to be right for the right reasons, meaning that we actually shift the attention of the model to the person. So that's the goal, and that's sort of the core contribution of this work. And our approach that we took is quite intuitive. So, if you see an image and you can see the person in there, we want you to be able to output a man or a woman. But what if the image has been sort of obfuscated so you can no longer see a person? And all you see is the context. There is the grass, there is the kite, there are some trees. We think you should not be confident about the gender prediction in this case. You should essentially be confused about, this could be whoever. So that's the core intuition. And we implement this by adapting our captioning model in two ways. We introduce two additional losses as we train it. So there is a standard sort of caption correctness loss, which is a cross-entropy loss, which is just applied to each word that we generate. But only for our gendered words, we additionally introduce confident loss. And for the other case with the obfuscation, we introduce the appearance confusion loss. And so the intuition behind these two is, in one case, we want to say the probability of the correct gender over incorrect should be higher. And in the second case, they should be equal. Essentially, we don't want to distinguish this to be either a male or a female sort of word group. And the math doesn't matter too much, but that's the high level idea. And with this very simple intuition, we get actually pretty good results. So we run this model equalizer on our data, and we evaluate it with several metrics that we come up with. So one is, like we said, there is this ratio imbalance, and the model makes it even worse. So we are capturing how close can we get to the true ratio in our ground truths. So lower is better, and our model indeed decreases that gap between the prediction and the ground truths. And also it decreases the overall error, the misclassification of men and women. Now, what's interesting, if we break down across the two genders, initially our model, our baseline performs like this. It does quite well for men and quite a bit more poorly for women. So in terms of the error, the misclassification. So after adapting the model with our equalizer objectives, we see a very common sort of very, very, very similar profile of the outcome of classification for both groups, for the majority group of men and minority group of women in this case. So that's an interesting observation, a kind of a more fair behavior as a result. And it also actually ends up looking at the person as we were hoping. So higher is better. So equalizer, more often attends to the person. And just to illustrate with a couple more examples, there is a man with an umbrella. And this is a good one. Here is a person, we predict a person walking a dog on a leash. And so we observed that our model starts to be somewhat conservative, but it cannot fully see the person. So it just kind of predicts a person instead of man or woman, which is, I think, more desirable than making an incorrect prediction. And so to sum up this part, we now see that communication really needs grounding. And the issues that lack of grounding might cause include, inappropriate, harmful, maybe offensive, maybe sometimes it's not super important, but sometimes, we care about these predictions more than some other scenarios. So that's the issue around communication and grounding. Now we're going to move on and talk about how, in addition to these components, we also need advice. So we are now talking about a different scenario entirely. We're talking about a self-driving vehicle. So imagine you are in a self-driving car and the car starts to brake. You really may want to know why, what is happening, what is the event, or what is the decision-making process that this car is doing. So it might be nice if the car could communicate to you immediately, that it slows down since it's about to turn left. That's the decision it is making internally, and so that's why we see this behavior. So there is two components to this textual utterance: the description of the action being taken and the explanation of why this action is being taken. So that is what we observed, and we decided to collect such human data to see, how humans go about explaining their own sort of driving behaviors. So we started off with this large data set in Berkeley, deep drive data, and we augmented this with explanations. So we asked humans to write things like these, the car is driving as there is nothing to impede it. So they annotate these video segments with these events, and we get a whole lot of these. Some are more interesting than others, like the car drives in the left lane in order to pass the school bus and so on. So we capture a whole variety of interesting events, occurring in these driving scenes, and there is just some statistics about the data. But what's actually the goal of the model? What are we trying to solve here? Well, the model is trying to predict the vehicle's future ego motion. So we're not per se building a car simulator. We are, this is all happening offline, but we are processing the video and outputting the ego motion, which is the acceleration and change of course in the next sort of frame. And the model internally has some kind of attention where it's looking in the scene and the attention shifts over time and spatially across frames. But the model is attending to some concepts clearly that matter for its control prediction. So what we introduce now is this explanation generator, which is going to enable our model to talk. So it receives as input these very controls that the model outputs, and then it goes ahead and talks about what the action taken is and why. But what is important is that we want to match the attention of this explanation generator to the internal attention of the vehicle controller. And the following example explains why this is important. So imagine there is the scenario where there is a red light going on across the street. It's fairly small. Hope you can see it. And so the model chooses to stop because it sees that red light. Now, if our explanation instead said, oh, I'm stopping because there is a pedestrian crossing, that would be plausible, but it wouldn't be accurate because that's not exactly why the model stops. So what we want is that the explanation indeed talks about the red light that went on. So basically, we want to tie, again, the attention of the controller to the attention of the explanation generator so that it's more grounded in the true sort of observations of the model. And the overall design is a bit more complex here, but what's important to us is we have this vehicle controller, which outputs the ego motion, and then there is two designs of building the explanations based on that. We could either strictly like align the attention of this module and this module by saying you have to exactly match the attention of the controller, or we could have a more softer alignment by saying we want to tie these two with the loss, but we don't necessarily strictly need to match the attention. And we find that in practice, that's actually beneficial to give the model some flexibility to see the scene in a way that it finds more useful. So let's see an example. So in the following, we'll see a video, and we're going to see at the top of the screen the human controls and our predicted controls. So the acceleration on the left and the course on the right. And at the bottom of the screen, we'll see how the model predicts the actions, descriptions, and explanations. And I hope the videos will play enough in sync so you can actually see what's happening. So the car is slowing to a stop. There was a stop sign. You can observe at the top how we are trying to match sort of human, like true controls with our predictions. Okay, so we're getting to a left turn. Now there is another rolling turn, stop sign. Finally, we keep driving because the road is clear. So you may find that these are not always the most exciting descriptions and kind of not the most maybe impressive scenarios, but this is sort of what's very common in driving. Oftentimes the model just keeps driving straight, or it needs to stop, or it needs to turn. And we don't actually often encounter very interesting or rare situations. But this is kind of giving us an idea of how this interface between the human and the AI could look like. And what we explored here is this notion that explanation is sort of like an extra loss we introduce in our model. So our model does not lose any performance accuracy, but it is able now to talk, which is just basically only a plus. And this is all good and great, but there is a catch. There's one problem that we found with this model. Since our data is captured in a way that there is not too many people in it, the model essentially does not attend to pedestrians and does not react to their presence. So we found that by analyzing both the visual attention and by analyzing the model behavior, that if there is a pedestrian in front, it just doesn't care. And so clearly we as humans don't think that's the correct behavior. That's actually very problematic. So how do we fix, or how do we reinforce the correct behavior, to pay attention to pedestrians in this model, and could we use advice for that? So think again about how we as humans learn and how we particularly learn skills like driving. So, here I showed the California driver handbook because that's where I am. But basically, we could read a guidebook, we could read the manuals, somebody could teach us, maybe a parent, and we gradually understand how this whole driving thing works, right? And maybe one of the first lessons we learn is that you really have to be mindful of pedestrians, like slow down if there is a pedestrian accidentally crossing, and so on. So that is like what we would capture not from experience, but just by learning the rules. So we go back to our data set that we collected and recall that it is in this form of the car slows down since it's about to turn left. So this description explanation pairs. And so what we noticed is that we could actually find another use for this data. What if we view these as observation action pairs? So now think about that. The model is about to turn left, and therefore it has to slow down. So we are reversing the order of these two, and now suddenly we have this useful knowledge from humans about, given an observation, what action to take. So we go ahead and use, this very same data to train a model in an advisable way. And so there is a high-level overview, and I will just go one by one by these blocks. So basically, the model, first of all, learns to summarize the visual observation, such as, I see that there is a heavy fog, interferes with my visibility. So it talks to itself, and that triggers the corresponding action that I should drive slowly. And this connection, this observation to action rule is being learned as the model is trained. So it's basically, purely language rules in this case. And now this action command goes back to the vehicle controller and tells this, you have to predict something aligned with drive slowly. And that will trigger the corresponding control being generated. So this is the overall sort of advisable learning design. And now the model can, reason in a way like, oh, if I see a pedestrian crossing, I will also stop. So we hope that this reinforces sort of a more reasonable behavior. And we do see in practice, in fact, that. So we see that the model predicts control much better. It can also pay attention to concepts that it hasn't before, like all these different important cues, road and cars and pedestrian area and so on, and less so to more like distractors. We also find that humans actually subjectively think that the model can see and recognize many more concepts reliably than before it was explainable or advisable. Last but not least, we actually try a more controlled experiment in a simulator called Carla, where we could create scenarios of our choice. Like we could create behaviors for our model which are challenging. And so basically the model gonna fail in certain scenarios. Like it will not stop at the red light or some other like under heavy rain and so on. So we could show now these scenarios to humans and try to understand what changes as the users get exposed to more and more information about the model. So like the first case, they just see the model's behavior. In the second case, they can also see how the model explains itself, the visual explanation and the textual explanation. In the third case, they get to see the advisable model, which first behaves, say, incorrectly, then receives advice, and then corrects its behavior. And so we are asking now humans, which model do you trust, essentially? And so we find, perhaps not too surprisingly, that they trust the advisable model the most. So it gets the best score as opposed to just explainable or completely unexplainable model. So that gives us a good sort of signal and hope that building these models with incorporating language advice not only leads to models which perform well and even better than before, but they're also more interpretable and they indeed gain higher human trust. And that is really one of the core ideas of, I think, around advisability, explainability, that we want to build better relationship with a human, right? So that was the two parts which we covered now, which center mostly around communication and sort of the corresponding issues of grounding and advice. And now we're gonna kind of shift gears a bit and talk about learning from language applied more broadly for vision tasks. Because what we actually see more recently is the certain paradigm shift that language is not just good for language or for vision language tasks, but language could also help us in many core vision problems as well. So we start with visual robustness, which is kind of when we are trying to make our models perform better under a variety of conditions. So first, we observe the following. In the previous, we have been always relying on human advice, right? So we actually had to go to a human, and the human had to write down what to do, what not to do, where to pay attention, and so on, and how to act. But these could be expensive to obtain, you could argue, right? And not for all scenarios you maybe have, such access to experts and so on. So what can we do in a more general case when we want to be able to tackle a variety of, visual concepts and in a variety of domains and so on? So our answer is, let's go and use these large-scale vision and language models. And the most prominent example, which came out in the last years, is CLIP. And so just because some of you may have not heard of this, so CLIP is the model which is pre-trained on a couple of, I believe, 100 millions of image caption pairs in a contrastive manner. So essentially, it learns to match images to captions. And it captures a lot of sort of general knowledge by doing that. And then what you can do, you can actually apply this model in a zero-shot way to new vision tasks. So how you do this, you take your particular problem, say you have classes like plane, car, dog, etc., and you create textual descriptions out of these, very simple, like a photo of a corresponding label. And now you're going to be matching these descriptions to your image embeddings. And so what the model is going to do is going to capture the similarity between each given, language prompt and the image embedding, and ultimately give you the one with the highest similarity, which, hooray, is a photo of a dog. So by doing that, you could now use vision and language to do basically any tasks in a zero-shot way. And so we are asking, can we now also improve visual robustness through language advice or language guidance? But we notice one important consideration is that CLIP is really powerful with many high-level concepts, but not quite with the more fine-grained classes. So you could imagine that by learning from a ton of data online, you could really understand well, a plane from a dog, but maybe you're not as good in terms of distinguishing very specific dog species, right? So that's the caveat. And so, to sum up, we have basically these two paradigms, our conventional CNNs versus these new vision and language models, which are very general, they use language, they can ground many high-level things, but they are failing at the fine-grained scenarios. And the CNNs, on the other hand, they can capture, very fine-grained features, but they might overfit to various biases and be prone to sort of these robustness issues. So let's talk about the specific issue we're looking at in this work is contextual bias. What is that about? So, let's say you want to classify land birds and water birds. Something a bit contrived. It's a slightly contrived data set as well, but it serves us well as an example. So, the birds which live on land versus the birds which live mostly on water. What your task is, that that's what you want, but all your data is built in a way that all of your land birds are on these foresty, green, land backgrounds, and all of your water birds just happen to have water in their surrounding. And so all your model knows is that, well, maybe this person wants to classify land from water. And it doesn't really know about your real objective, which is to classify the birds, right? So in a test time, if you're now suddenly given a land bird which appears in the context of water, well, you're going to make an incorrect prediction because there is water. So, these are synthetic images made to really make that point super clear, but this is actually something that people who work with sort of, like naturalists who work with various animals in different habitats, they actually say that this is a realistic problem inspired by some real world scenarios, that you want to separate the concept you're learning from the context or habitat that it's in. And so what we are saying here is that let's keep the CNN. We're not, removing the CNN here. We are keeping our CNN, which is trained on these images. It predicts labels, but it might be flawed because of this bias, right? So we know that maybe it wasn't looking at the bird sometimes, but was looking at the forest or other features which are present, which it learns essentially because of how the problem itself is biased. Now, what we're going to do, we're going to tell our model that our problem is to classify birds. So we're creating this language specification of the task, which is going to inform our model what to pay attention to. And so we are just creating very, very simple prompts, a photo of a bird, an image of a bird. You could even try more fine-grained ones, but we actually find in practice it's sufficient to just tell the model that the task is about birds. We don't need our vision and language model to have the full knowledge of, all the fine-grained scenarios in our data. So all we are doing is telling our model, tell me where the bird is. And our vision language model, like CLIP, can basically relate this prompt to the photo and produce an attention of its own, essentially localize the bird in this picture or ground. And all is left for us is to say, I want my CNN to pay attention to the same region as what my vision and language model is telling me. So it's a high-level guidance about the task, right? Translated into spatial attention to hopefully lead this model away from all these contextual cues, which are actually irrelevant to the task. And so we're going to be evaluating this on this very data set of water birds, which is completely biased. So, at training time, all these land birds are on land, all the water birds are on water. And at test time, it's all mixed in a balanced way. So you can encounter all 4 scenarios equally. And typically how it's done in literature, you evaluate per group accuracy and like worst group accuracy. And so we find that, first of all, our method in blue here performs the best across a range of baselines, in particular, improving over all the CLIP versions that we consider, which is CLIP zero shot and CLIP fine-tuned, which is basically does worse because either it doesn't fully know these fine-grained concepts or it becomes similarly biased by adapting to the biased training data. And so we indeed see the advantage in combining both of these ideas of still keeping the CNN, but just guiding it with the language advice. Another example, so the original images, the images with the language advice grounded into the picture, the vanilla CNN incorrectly attending all over the place. And after we guide it with our advice, it starts to look at the bird. So that's the message. We can turn this high-level language, specification of the task into spatial attention, which then guides our CNN away from bias. So this is us exploring how essentially learning from language, in this particular case, can aid visual robustness. And so the last part for today, we're going to talk about learning from language for visual transfer. So, okay, so like we just talked about this very cool idea of using these vision language models that already have a lot of knowledge in them, but we did notice that they lack some knowledge, right? So they might be really good with high-level concepts, but they lack some of the more fine-grained understanding of object categories. So could we do something about this? And the answer is, well, there is a lot of knowledge out there, right, already captured by humans in many external resources. Think Wikipedia or similar. So this encyclopedic structured knowledge is, we argue, a key to making our models sort of even more knowledgeable and even more useful. So the problem statement we're going to be looking at specifically is zero-shot learning. So zero-shot learning has been explored traditionally in the sense of class-level transfer. So like you've learned your 50 classes, and now you want to do well on some unseen, 50 classes. However, more recently, especially with this advance of vision language pre-training, we see this new paradigm of task-level transfer. So you train your CLIP model, let's say, on a huge amount of image captions, and then you test it on entirely new tasks, right? It was never even trained on. So new tasks, new data sets. And so we're interested in this task-level transfer as we think this is really where the future is. And so, but when it comes to modeling knowledge, we have seen a lot of advances in prior work in the traditional case. So people have explored how to associate essentially seen and unseen classes to each other through some additional knowledge from, say, attributes or learned embeddings or knowledge bases. But there was really nothing yet explored in this task transfer setup. So this is where this project lands. Again, how do we enhance our task level transfer with external knowledge? And here's an example for you as a human, So you're coming to a Japanese restaurant for the first time ever, and you see the menu. There is no pictures. There's just some dish names. And would you want takoyaki or sashimi? Well, no idea. So maybe that's a problem. What could we do in this case to essentially help us make a better choice? When ordering our meal. We could use knowledge of the waiter. The waiter could come and explain, what these are. So the waiter could just tell us, there is a bowl-shaped Japanese dumpling, that's takoyaki, and, raw fish or raw meat slices is sashimi. And then we can understand and recognize when we see these visually, right? Since we have a lot of prior knowledge about what all of these concepts are. So we humans, we don't memorize things sort of like in isolation. We have really a lot of structured knowledge with relationships between concepts in our minds, which allows us to generalize to also new concepts. And so we're asking if we could bring this same capability, for AI task level transfer. So we're going to be taking in the following the kind of the look at the traditional approach to learning with language and adapting it to learning with language and knowledge. And so the traditional approach is like this. You have collected, your image language pairs, sort of most recent. I mean, it's already become traditional since 2 years. And so for example, you have data like this, a bunch of images and descriptions, and you just learn from that. Like I said, with Clip, you could do that. And you could then go and test it on a variety of, downstream vision tasks. So we take another step. We say, what's the key concept of this description? And we call this a query. So sashimi, for instance, becomes the concept of interest. Now, we're going to query a knowledge base. And now here is where the knowledge augmented learning comes in. So with that query, we go to something like Wiktionary or WordNet and basically ask them, what's sashimi? And this could be expressed in a variety of ways. From WordNet, we could get some hierarchical information, like sashimi is an example of some food, etc. We could get a definition that it's a very thinly sliced raw fish, or from Wiktionary, we get even nicer, more detailed definitions like these, which we find in practice to be most useful for us. So essentially now we have acquired this additional text, right, which complements our original caption. So what are we going to do now? When we train our model, we're going to basically enable it to access that knowledge base and extract the particular bit of knowledge. And then we're going to be also using that knowledge when we evaluate concepts. So we essentially just augment that standard image language learning pipeline by introducing these definitions also as part of the language prompt, so that the model learns them, in the training stage, and then also can access them during the inference stage. And then we can go and try, apply this to a variety of downstream tasks. We evaluate across similar data as what the Clip work did. So particularly there is transfer to ImageNet and 20 more very broad public data sets. And we built sort of, our baseline is this work UniCL, which is trying to unify learning from labeled images and learning from image caption pairs. But to kind of summarize, the key finding is that we could get a total of 2 to 5% improvement across that baseline, which is without knowledge, across a wide range of these tasks. Again, here is 20 different data sets. We're just averaging the performance. And we also show sample efficiency with knowledge. So when we compare these two models, one is trained only with 15 million image caption pairs, the other one with 28, almost half the size, we actually can match performance, which shows that knowledge gives us some additional leverage, right? So we don't need as much data actually to train with, which is intuitive what we would expect. And so last question we're gonna answer, when does knowledge help and when does it maybe not help? So if we analyze these 20 tasks, right, which are really broad, from flowers to pets to even some geographical tasks like country classification to cars, all the way to satellite imagery, basically we see that in some cases we see a big improvement, and in very few cases we actually see some disimprovement, some drop in performance. So what we found is that the most successful scenarios is where we have these more fine-grained data sets. We also have pretty good coverage of concepts in our knowledge basis, so we can do really well and boost performance for these rare fine-grained concepts. But unfortunately, in the cases when either our knowledge is like poor in quality, the coverage is not so well aligned, with these tasks, or there are some not useful or spurious words in our definitions, then the performance can actually go down. So clearly the quality of the knowledge matters. But the key message is we can further enhance basically this idea of learning from language by also learning from knowledge. And that benefits our large-scale pre-trained models. And so we are almost at an hour, according to my clock, but maybe that's incorrect. So basically, we talked about these 4 different topics today, but just to summarize the key takeaways from each one is we showed how communication needs grounding with the example of correcting gender bias, and so being right for the right reasons in the end, so grounding helps to communicate things more accurately. We also showed that you still need advice to achieve better performance and also better human trust. Finally, we show how learning from language can benefit visual robustness on an example of showing how we could tell the model what the task is and so guide it away from the contextual bias. And finally, we talked about visual transfer, where language knowledge can help us basically build ultimately even more transferable general purpose visual models. And obviously, all this work I haven't done alone. It's been a huge number of collaborators and amazing authors shown here on the slide, some of them, not everyone. So I covered these 5 papers today. And just to kind of wrap up, we could take the last look on this entire sort of space and think about what maybe is next for us and where is this moving and what is sort of my vision for this research direction. So we talked about, in the beginning about we want these AI models of the future that can communicate, learn from language, and really the core linchpin, sort of the very important idea is grounding. Because if we can't ground things correctly, then our communication suffers and also learning from language may be compromised. We have also observed some limitations to our work. One was that we sometimes need human expertise, human supervision, right? To give us explanations, to give us advice. This could be hard to scale, and transfer to other scenarios. So that's one caveat. And the other one was that, we use these large scale pre-trained models, which are really good at high level concepts, but we are still sort of limited by how expressive our advice can be. And like, we are limited to somewhat simple prompts so far, at least in general case. So how do we push this forward? And first of all, where do we actually want to go? So I argue we want to go towards, even more open-ended scenarios. We want to be able to tackle a variety of downstream applications, arbitrary concepts, understand relationships between concepts, which is very important, and bring in the world knowledge. And we've seen a little bit of that already in that last part, how to bring more knowledge into the models. But so all of these are desired. Sorry, I think this jumped over. Oh, I guess this is actually an example. So an example, maybe I'll keep this brief. This video just show us, I hope this is going to be synchronized. You're going to see a video of this little squirrel coming in somebody's backyard and finding some nuts, apparently, who some nice human left for the squirrel. And then there is more animals coming, there is some birds. And like we as humans, what I'm saying is we can interpret that scene, very complicated scene, in a very structured way, and extract a lot of knowledge out of this and access our own prior knowledge about what's happening, even what's about to happen. You could maybe anticipate that these birds may not like each other, it might be competitive because there's a food source, and also the squirrel might come back again and chase them away, and so on. So we can make a lot of inferences about this video, tell a whole story about it, if you will. And my point is that these models of today are far, far from capable of doing these things that we humans can do. So what they lack essentially, and what we have, is on the one hand this grounding of these arbitrary complex things like relationships and world knowledge, but also compositionality and structure. So this is some of the important, part here, important limitation of our existing large-scale models, that oftentimes compositionality suffers, that they can't sort of combine individual atomic concepts into larger concepts. And also structure means that frequently we deal with models which are just like a huge monolith, black box, foundational model, but we don't know what's happening within it. There is no modularity. We can't understand if it has its own biases, or what's the best way to kind of use it in our particular downstream application. And so these issues of compositionality and structure, I think, are critical. And one example to illustrate compositionality is on the recent image generation model DALL-E, which, as the authors discuss in the paper itself, struggles with composing scenes like a red cube on top of a blue cube. Very simple, you would think, but the model often predicts some incorrect images. I even have one of my own here. A cat in a blue hat talks on a red phone. And so one of the four it got right, but I think it's more chance than the sort of the rule, that more often these models get confused about which attributes belongs to what object, or the relationship gets messed up or something like that. So I'm saying that we need models which are more compositional and more structured. And so I specifically, my vision for this line of work is that we're going to build foundational grounded models, compositional and structured, that we could then inject their knowledge into our downstream AI to really enable these capabilities that I talked about today of communication and grounding and learning from language. And sort of to close the loop, we also want to go back and say we might still need human supervision, but hopefully less so. Hopefully we could become more sample efficient with all this knowledge. And basically, that's sort of my vision for AI of tomorrow. But with that, I should really wrap up now, I think, and happy to take any questions. Thanks so much.
Great, Anna, thank you so much for such a great presentation. I think, like, personally, the way you laid it out on how the machine are learning, it actually explains and describes how we humans do learn, with the concept of grounding and then the advising, avoiding contextual bias. It so much reflects our human learning. Before we start asking questions, I would ask our audience to participate and go into Q&A section of the slido.com, the resource that we use. Ask your question and do the upvote for the most interesting ones. Also, yeah, let me read them one by one. Bogdan is asking, during the last task, which amount of dictionary data did you use? Is it possible to quickly handcraft this amount of examples if needed?
So in this case, we experiment with several knowledge bases, from like the entire WordNet, which kind of is closely aligned to ImageNet, so it made sense there, to Wiktionary, which is much broader and covers more concepts, and there particularly we extract these definitions of concepts. I would say the more in this case is the better. So this knowledge is really like I was trying to show in the last examples there, that if your knowledge coverage is not matching your downstream tasks, then the knowledge might not be as useful, or it might even be harmful. So it's not something I would say easy to handcraft. I think you would need to access pretty broad sort of encyclopedic resources. And also some limitations of those even are that even they sometimes don't give you enough sort of fine-grained information. Like they might not care about some distinctions that you might care. So you might still need to kind of like for each particular domain, maybe augment it with your own data and so on. But yeah, this is a good question. So the quality of knowledge is central, I think, to making that successful.
All right, thank you. Next question from Igor, who's asking about your last concept of learning with additional knowledge. Is the final model in inference time the same as CNN that learns without the knowledge? Is the knowledge passed on only loss at training time?
So the model is actually not per se a traditional CNN. So like we're building on top of this literature of already language enhanced models. So these are typically, contrastively trained models. Our particular one is actually trained in a unified manner, but think about a model which already knows how to interpret text. So it leverages language in training and in inference. In training as kind of like part of the label. So it learns to match that language to images. In inference, you could, again, build these language prompts and score them against your images to get like what one, which one is the most appropriate one, similar to how this sort of recent clip style approach works. And so you use knowledge both in training and in inference. I think that answers the question.
Yeah, I think it does. Next question comes again from Bogdan, who's asking if those models are the buildups of the existing trained models.
So in the first two parts of my talk, I talk about specific examples which are more like, I guess, pre-arrival of foundational models. And in the last two, yes, we are seeing now this trend that these large-scale pre-trained models becoming really the very powerful tools that we could build upon. And in one case, we show that we could basically combine that with the conventional CNN. So we use the guidance of that large-scale model to direct the CNN's attention. In the last example, we showed that you could actually build a better large-scale model of its own by injecting more knowledge into it. So for better task level transfer. So, but the trend is moving towards leveraging these large-scale models for a variety of purposes downstream. Yes.
All right, thank you. Next question comes from Petro, who's asking what data you have used for training. Data sets, backbone, if yes, which?
So I'm not sure to which particular part this might be referring. It might
That
be
was the one at the very
easiest
beginning.
You think this is about the first
part? It was first
for the
part.
captioning. Yeah, so I mean, everything we use is publicly available, and we have specific, instructions and references in all the papers. I don't know if I guess the slide with the papers might be helpful for you if you want to chase down some details. But for captioning, we use the standard Microsoft Coco image dataset with captions, and in that case, the backbone was a somewhat traditional captioning model. I actually don't know anymore the specific details. Was it built on ResNet or not? But yeah, it's not super important, I guess. The idea is sort of a more general one, that in that case, models exhibit bias. And apparently it's still true, because I tried the very recent state of the art and it still does the same thing. And so it's kind of regardless of a backbone. But yeah, I would recommend, if you have some specific question, Petro, then maybe just check out the papers. Hopefully you can find that the details there.
Thank you. Next question comes from Nazar. He's asking about which human annotation resources were used for those improvements. How do those annotation look like?
So we talked about human annotations so let's talk about the self-driving example, for instance, right? Where we actually collected the descriptions and explanations of driving behavior from humans. So there was nothing too surprising there. As many others, we used Amazon Mechanical Turk. But what's really important, that was to create the interfaces to let humans annotate this in a very convenient way for them and prompt them in the right way to give us a description of what's happening in the video and the explanation. I'm thinking if there was another part of the talk which touches on human annotation or not. I guess in the last two parts, the whole point is that we no longer require any additional annotation, but we are really leveraging either these large-scale models or existing large-scale encyclopedic resources. So there is no more human involvement to label anything in there.
All right, thank you. Thank you, Nazar. Bogdan, again, our active participant, wants to share some cool resource about Mesa optimizers. It's not a question per se, just Bogdan wants to share a YouTube link, how the way the human and machine objectives differ. Encourage everyone to trying to copy the link and see it for themselves. Any comment?
I haven't seen this, but I could imagine what this is about in general. I would say that yes, many particularly harmful situations can arise in sensitive, in sensitive problems which concern humans and human livelihoods, right? Which might lead to unfair or biased decisions because models are trained to optimize, certain objectives which we as humans maybe, which wouldn't align with our values necessarily. It's a really important and big issue. And I haven't talked specifically about fairness in that sense today, but I think, there is something about, is the model behaving correctly or not, which is more what I was talking about. But there is also another thing, how well is this aligned with our values? And there is a lot of very interesting research out there. And I think, advisability may provide us sort of one way to address that. If we could tell the model, this is the incorrect behavior and perhaps guide it away from it. But I'm not arguing this will solve all of our problems necessarily. So we might need to look closer into human values and how they match, the objectives that we set for our machines.
All right. Next, Bogdan is mentioning Whisper, the recently launched project on the quick transcribing of multiple videos, which was used for YouTube. Huge field of work, Bogdan says. What do you think?
I don't have too much to say to that, I think, right now. I think transcription is still a work in progress, pretty much. After all the years, I think we are still not always doing a very good job with automatic transcription. So look forward to seeing this get even better.
Okay, thank you. Thank you, Bogdan. We have another Bogdan in the audience who says that seems like you're basing a lot on attention models. Can you see possibilities of the usage of another common types of models to implement some features and or problems like scaling transfer problem mentioned in the end? If so, which ones?
So maybe, let me think what this might be particularly referring to. So yeah, we use attention in particular when we are interested in more explicitly looking at grounding within models, right? To understand where they're looking and if that matches to any language that might be aligned with that. But I think the two components that I talked about at the very end of the presentation, the compositionality and structure, I think are these important directions to focus on. So in particular structure, more structured models essentially, or more modular models, where you could maybe tease apart the different parts of the model which are responsible for particular tasks or subtasks, right? And I feel like with these more structured models, we would also enhance how well we could interpret them. So maybe that is not like immediately answering your question, but perhaps, modular networks or more structured models is where I would suggest to pay attention to.
Thank you, Bogdan. Natalia is asking, how long would it take to train the AI using GALS training with task level transfer? And can both class level and task level transfer be combined for higher adaptability? Which AIs are the fastest learners?
So I think there's two different things being combined here. So the GALS approach was what we used in the visual robustness case, which was about the adaptation story, where we basically show how we could overcome this contextual bias issue. And that is very lightweight. That doesn't add too much overhead over just training a CNN. The other story was the task level transfer and so on. Well, there's going to be some overhead, I guess, because we need to access the external knowledge and kind of augment our data with that. And then, but not a very significant overhead, I would say. I can't really comment on, particularly speed in this case. Sorry, what was the particular class level or task level be combined? So in class level transfer, typically you are within a certain domain. Say you are interested in classifying, animals, and there is a subset of those that you've seen and subset that you haven't seen, and you want to generalize to those. With the task transfer, you really are dealing with multitude of domains and types of imagery and so on. So it's a kind of different priority there. The goal is really to acquire a much more general representation to handle, the variety of data sets. Could we combine both and at the same time also do better on the more fine-grained cases within each domain? I guess so, and that could be a promising thing to look at. We haven't really explored that direction yet. Which AIs are the fastest learners? Not sure. I mean, all of these models are quite data hungry, and some of them are extraordinary data hungry, and things are just scaling out of proportion these days. So I think if you want to work on something really impactful, this could be how to make more sample efficient models, how to make them not be, so crazy large, and make it more feasible to actually train for everyday users, as opposed to only biggest corporations can train these models. So I think, there is a big open challenge in making these models more efficient, definitely.
All right, thank you for your answer. Thank you for your question, Natalia. One of the last questions comes from Victor, who thanks for the talk, and he's asking if the communication with advisability achieved solely by attention mechanism.
So again, with the advisability, there are different. I think the overall idea is very general, that you want to use language to tell your model something useful about the task, about what's the right behavior, something along those lines. So the key for advisability is language. But then you introduce the language in a variety of different ways. In one work with the driving, for example, we really reinforce this entire rule-based system, right? Which says, if you see this, act as follows. And that is introduced within the training cycle of the model. In the other works, we used language to mostly ground the CNN towards the right concept. So it was mostly about localization. It's not per se an attention mechanism. We actually look into more sort of introspective techniques there for where the CNN is sort of more causally looking at. So it's not all about attention, but if by attention you mean grounding, then I think, yes, grounding is very important, but you have to see each particular scenario, how you actually, what goal you set to make use of the language advice. And yeah. not a universal solution.
All right. Thank you, Victor, for your question. Thank you for the answer. Helena and Bogdan are thanking you for the presentation, for the talk, and for the answers. The last question comes from me. On behalf of those 50% learners, I would ask you to advise some good book or resource to read on the topic. Which one is your favorite?
Oh my God. I think the issue is that the topic itself is, like in its entirety, I mean, it's not a new topic. The vision language field existed now for probably over 1 decade, probably I should say 2 decades at least. But the most recent ideas that we are discussing here, and the cutting edge, it's just happening now. Basically, there is no book written, right? Like, we are looking at some of the things. If you think of what we've seen in the last years, from DALI and CLIP and diffusion models and all these things which are happening now, and every day there is new and a new cool thing. I don't have a book pointer. I think we just try to keep an eye on what comes out new and try to read and read and read all the papers which are coming out. And it's it's a lot of reading that one needs to do. Obviously, one has to filter a bit, but yeah, there is no book, unfortunately. Maybe in 10 years we'll have a book about what's happening now, but not right now.
All right, interesting take. I will go back to the slides and find one with all this list of papers that I should read. Yeah, thank you so much, Anna. Very, very interesting session. I hope you, the audience, enjoyed this session as much as I did. Again, thank you, Anna.
Thanks,
marvelous.
everyone. Thanks for the engagement. Sorry, just the audio lag. Thanks for all the questions and the engagement. It was wonderful to interact a bit more with people, although I regret not seeing you all, but this is the best we can have right now. And yeah, and just wanted to say a few words that I'm also Ukrainian, and I'm with you in this, at least in my mind, and really hope for, for the better future for all of us and the peaceful one. So thanks for having me.
Thanks for being there, Anna. Thank you for supporting us. And audience, this is the call for you to keep donating to our cause for the victory. Next week, we have a talk from Yujian Wang, assistant professor at computer science at University of California, Santa Barbara, director of Scalable Statistical Machine Learning Lab. Yujian will share his stories on practical reinforcement learning, offline data, and low adaptive exploration. In order to help us, your organizers, I would like to run a small poll to understand how you like this session. On behalf of our team, I would like to say thank you for being there. See you next week. Check your inbox for the updates. Keep donating for the victory. Slava Ukraini. Bye.